All right. So let's work this problem. This is going to construct the influence line for the moment at C. C right here is in mid-span of this, and then we have an overhang. So our previous kind of strategy has been to imagine the structure cut, and we're going to get the moment there. Which side do you want to work, the left side or the right side? Yeah, the left looks like a good one. And since I want to go left, then I'm going to be interested in finding AY as part of that free body diagram. And I won't be so concerned about BY. So let's go ahead and again construct a free body diagram for this particular case. And I'll be concerned about my unit load for my moving load at some distance x from the left, and then I'll have the reaction I'm looking for the rest of my work, AY and BY. So how do I find the reaction at AY for this scenario? What's the easiest thing to do? Should I sum forces in the y direction? No. Should I sum forces in the x direction? Well, you can. That won't really get you very far, will it? So we need to sum moments about B. So again, right-hand rule. Let's sum the moments about B and set it equal to 0.
Is that force to the left of C?
It doesn't matter right now. I know that this distance is 10, so what's the distance from B to that force? 10 minus x. And then what would this little distance out here be? 5. So with that, let's see if this is going to work out. So some moments about B, looking at the moment of the unit load about B, it is positive with a moment arm of 10 minus x. And then I'll have my reaction at AY, which creates negative moment, and that has a moment arm of 10. So it looks like when I solve for AY, I get 10 minus x divided by 10, which could easily be 1 minus x over 10, if you like. That kind of makes sense. When x is equal to 0, it says AY is 1. That means the unit load would be right over A. That seems reasonable. And then as I move over to, say, x equal 10, where the unit load now is right over B, well, x equal 10, that's 1 minus 1 is 0, so there is no reaction at A when the moving load is at B. Now, when the moving load moves out on the end of the cantilever, when x is, say, 15, what happens? You plug in 15 here, you get negative a half. So as I move out here onto the free end, my reaction at A changes direction, negative, and it's half the load. So it's having to pull down to keep the beam in equilibrium. That makes sense. So I feel pretty good about the AY. So our first case, since we're cutting at C, is when the unit load is anywhere on the left-hand segment, which would be a position between 0 and 5. And when I do that and draw the free body diagram, I have the unit load at some distance x. I didn't give myself enough room, so I have to draw this in here. This would be 5 minus x is that distance. I would have the reaction at AY, which is up of 1 minus x over 10. And then I'll have the internal moment that I'm looking for, the moment at C. And of course, this segment is 5 feet long. I'll go ahead and draw the shear in there, just so you don't think I left it out. But we're not interested in the shear for this problem. We just want the moment. So how do we find the moment at C for this free body diagram? Well, whenever we want moment, we sum moments. So let's sum moments at the cut. In this particular place, the cut is at C. And make sure this free body is in equilibrium. So starting here with the moment, the internal moment with my sign convention is positive. The moment due to the unit load about C is also positive. There's the force, and the moment arm is this little distance here, which is 5 minus x. And then I have the reaction, which creates negative moment, 1 minus x over 10. That's the reaction. And it has a moment arm of 5. So now I solve for the moment at C. Let's see. There's a positive 5, and then there's a negative 5. That cancels. There's a negative x, and then there's a positive 5x over 10, which is half x over 2. So I've got a negative x plus x over 2 gives me a negative x over 2. When I throw it to the other side, I get positive x over 2. I think. Check that for me. That look right? So I know that when the unit load is on my beam between 0 and 5, this is the way the shear at C will respond. What about when it's over here? Well, that would be when the unit load is in the position between 5 and 15. So I'm still working the right-hand side. So that free body is unchanged in terms of the geometry. It's still 5 feet. Oops. It still has the reaction at A, which is 1 minus x over 10. I still have the positive shear force and the positive bending moment. And again, it's still 5 feet. What's different? Well, the unit load is now not between 0 and 5, it's between 5 and 15, so it's over on the right-hand side. So it's not on this free body. So again, we're looking for the moment at C, so I'll sum moments sum moments at C. And make sure it's in equilibrium. So again, I have my assumed positive bending moment, which is positive in my sign convention. And I have the reaction, which creates a negative moment. It's 1 minus x over 10 and has a moment arm of 5. So the moment at C is just this thing. It looks like it's going to be 5 minus x over 2. Did I do that right? So I just need to plot this thing. So I'll plot this equation from 0 to 5, and I'll plot the second equation from 5 to 15. So my influence line for moment at C will look something like this. So I'm interested in 0 to 5, and then 10 and 15. So we'll start with the first equation. At x equals 0, it's 0. At x equals 5, it is 5 over 2, and that's linear. So that is the graph for this equation. So now I'm going to graph it from 5 to 15. So I put in 5 here, and what do I get? I get 5 minus 5 over 2, which is still 5 over 2. So it gets the same value for the moment. When I put in x equal 10, I get 0. When I put in x equal 15, I get minus 5 over 2. Okay? So now you can see there's a position. If I'm operating in 0 to 10, let me put some ordinance on there. So when my unit load is moving anywhere from 0 to 10, what kind of moment at C am I creating? What's that positive moment? But when I start operating from 10 to 15, what kind of moment at C do I create? Negative. I think that makes sense too. As you operate in this mid-span here, you would expect this part of the beam to curve upward, which is kind of like our smiley face, positive moment. And if you go out here on the end, this structure is going to curve concave down, and you'll see negative moment. And you can get a maximum value, really, that has the same magnitude, just a different direction. So any questions about that one? I think that's moving more towards like an exam problem. Okay.